One more example problem. A sheet of glass with index of refraction of 1.5 is coated with a 503 nanometer thick layer of oil that has an index of refraction of 1.42. For what visible wavelengths of light in air do the reflected waves interfere constructively? There may be more than one. Okay, so our sheet of glass coated with a 503 nanometer thick layer, this is our D. So this layer of oil is the film. The film is the oil that has an index of refraction of 1.42. That is on this glass that has an index of refraction of 1.5. Then I still am just going to assume air out on the other side. The film is oil, the surface is glass. So comparing these ends, n of the surface, 1.5, is greater than n of the film, the 1.42. So that tells us what column to look at on the table. When I look at the table, there's a lambda c of 2nd over m, of 2nd over m minus 1/2. And that's under this heading of n of the surface being greater than n of the film. To determine which of these we want, reading the problem again, it wants to know what visible wavelengths of light do these waves interfere constructively. So we want the constructive interference equation. So lambda sub c being the 2nd over m. And we know m, there's multiple values of m. That's what m is representing. There's multiple wavelengths that can constructively interfere in this oil layer. This is specifically asking us about the visible wavelengths. I don't know those off the top of my head. So on page 2, we have the table at the bottom of the page that tells us that red is approximately 650 nanometers and violet is approximately 400. Now, you might remember previous example, we dealt with a red that was greater than 650. This is just an approximation. So let's look in this range and see what wavelengths constructively interfere. What this means is we have to keep putting in m values until we find all of the wavelengths that fall in this range. So n, always the index of refraction of the film itself. D, 503 nanometers, that's how thick this layer is. So the numerator is always going to be the same. What we're going to vary is m. If I put in m of 1, I'm not going to round my answer yet. This m of 1 gives me a value of 1429 nanometers. This is not visible. It still constructively interferes, but we wouldn't be able to see it because it's not visible light. If m is 2, so again, the numerator is the same. Oh, seriously, 2, not a 3. So if I divide that by 2, I get 714. Still not in this range we're shooting for. M equals 3. So all the same stuff over 3. Now I'll write it out. 2, 1.42, 503. 476 nanometers. This one is in this range, so this one's visible. But I have to go to n equals 4 and see if this is also visible. You might recognize that it's not going to be, but always be sure that you prove that to yourself, because it's possible that more would interfere. So 357 nanometers. So in this particular case, it is this one. So approximately 480 nanometers if we're going with the 2 sig figs on the N of glass. This is what constructively interferes. Only one wavelength in this particular case would constructively interfere. Depending upon the problem, there are situations where more than one would interfere. And that's why you want to keep going through M values until you are sure that you've gone past the entire range of visible light.